Let's now take a look at Green's theorem in flux form rather than circulation form. So in the circulation form, we added up the twistiness at each point, and we saw, well, we could just trade that for looking at the circulation around the curve C, which bounds R. Well, now we're going to add the divergences, okay, the sort of expansionness at each point. Okay, here you see, like, I use this green one, this green square, just to take a look at. It has arrows coming out to represent the sort of expansiveness. But each of these would also have expansiveness. And here you could see that, you know, they'll collide at the boundary. And you could sum all of that expansiveness and contractness, okay, around the region. Or maybe we could do something else at the boundary, okay? And that something else is actually a flux line integral, okay? So you can trade the 2D divergence in the bulk, which is the derivative in the bulk, for an operation at the boundary, which operation here? The flux line integral, okay? And that's the statement now of Green's theorem in flux form. And of course, as a reminder, we are in R2. Here I drew the X and Y axes. We are in R2. We'll talk about how to abstract into higher dimensions, but we are sticking to R2 over here. We are working in the plane. This is a double integral, and that's a line integral. So let's look at a very quick example. So you take a look at this a line integral here, okay, and this is a line integral, and it's just written in this form, but you could always switch out dx and dy, okay. And we want to take a line integral over C of the boundary of this disk, okay. So this is a circle of radius 2 centered at the origin and going in the counterclockwise direction, okay. We're going to use Green's theorem, so we don't want to compute this. This is going to be very hard to parameterize the curve and plug it into here and compute the integral. So why don't we instead use Green's theorem? So instead of computing that line integral, what we'll do is trade that for a double integral of the divergence. And by the way, this here is in the flux form, all right? If you'll recall that this expression could be written as line CF dy minus G dx, which is actually equal to FG dot dN, okay? So this is already written in the flux form if we choose this for F, okay? So we're going to choose that for F. And if we choose for G, this, okay? Then we already have it in this sort of, and we didn't have to do that. I mean, some of you may have been wondering, what if you just switch these around and then you would have, you know, dx first and then dy there, and you could trivially switch them around and you could write it in, then it would look like a straight line integral, and you could use circulation form. You'll get the same answer, and it's with the same simplicity. I'll have a word about that at the end. Okay, so using that, so this is already in a flux form. Okay, here it is, f dy minus g dx for a vector field f that we chose this way. And here it is, as you know, I just wanted to formally show you that this indeed can be written as a flux, a vector line flux of some vector field, which we had appropriately chosen. And now here's the statement of Green's theorem right there in that equal sign. We're going to switch that out for the divergence of this, the 2D divergence of this vector field. And so we're going to take the partial derivative with respect to x of f and add it to the partial derivative with respect to y of y, of g. And so you get this term here, and now you're left with a double integral here, and you can use Cartesian coordinates for that double integral, but it's much easier at this point to convert into polar coordinates and compute the double integral. This last part, converting to polar coordinates, is not really related to the Green's theorem. It just happened to be a way that we could compute the double integral. Here's the substance, though, of Green's theorem. It's that this thing here is equal to this thing here as we've defined it above. So you do that straightforward integral and you get 96 pi. And a quick word here about the ambiguity that, hey, you know, couldn't you have written that as a line integral rather than a line flux integral? Yeah, absolutely. In fact, you could always trade a line integral for a vector for a line flux if you're willing to change your vector field. So we could, this here, okay, is equal to this here. Okay, so if we switch out f and g and multiply one of them by -1, then this line integral can be the line integral of f can be written as the flux integral of that vector field where f's components are switched out. Okay, and here's the summary of that statement. And so this works also in reverse. You could always change the a line flux for a line integral. Okay, vector line flux integral for just a vector line integral.